Hello everyone. We are Group 15 and we are presenting on inventory decision in Dell supply chain in part 1. I'll begin by setting the context for this entire presentation and I'll be explaining why this research exists in the first place. So, to understand the problem we are addressing, we need to first understand the core strength of Dell's business model. Dell is globally recognized for having perfected the direct model. So instead of building computers based on speculative forecasts and then pushing them into the market, Dell waits for real customer orders and then builds to demand. So this allowed Dell to dramatically reduce finished goods inventory and respond faster to changing customer preferences. However, what this research reveals is something counterintuitive, but it is very extremely important. Dell did not eliminate inventory, it just displaced it. So rather than holding excess inventory on its own balance sheet, Dell pushed inventory upstream into its supply logistics centers. And they're also called revolvers. So these revolvers sit very close to Dell's assembly plants and act as buffers that allow Dell to pull components every 2 hours in response to customer orders. So now on the surface, this looks like a highly efficient just-in-time system. But when we examine how inventory decisions were actually made inside these revolvers, a serious inefficiency emerges. So Dell used a uniform 10-day inventory rule for all components. This rule was simple. Every supplier had to ensure that roughly 10 days of inventory was always available in the SLC, regardless of the component type, its volatility, or its economic characteristics. And this is where the strategic failure begins. So, in the PC industry, components are not equal. Some parts, like power cords or metal brackets, are still stable. Their value does not erode quickly. Others, such as CPUs, memory chips, and graphic components, they are very high velocity, high depreciation items. So, these parts lose between 0.5 and 2% of their value every single week. So, applying the same 10-day inventory target to both categories is economically irrational. What the research demonstrates is that this rule of thumb completely ignored demand volatility, lead time uncertainty, component depreciation, and supplier cost exposure. The irony is that Dell's internal metrics looked excellent. Finished good inventory was low, assembly lines rarely stopped, service levels were high, but suppliers were bleeding. So, under Dell's vendor managed inventory model, suppliers technically owned the inventory, but Dell dictated how much inventory had to be held and when it could be moved. So this created a very dangerous misalignment. Dell controlled inventory decisions, suppliers absorbed holding costs and depreciation losses. So this asymmetry created friction. Suppliers were forced to carry excess stock of rapidly devaluing components simply to meet Dell's static targets. So the research frames this as ownership without control, which is one of the most destructive incentive mismatches in supply chain design. So now why does this matter strategically? Because inventory is not free. Every extra day of inventory sitting in a revolver represents a capital tied up, a lost pricing power for suppliers, risk of obsolescence. And when suppliers suffer, Dell eventually pays the price through higher component prices, less flexibility, strained relationships, and also reduced innovation collaboration. This brings us to the real insight. The problem was not operational, it was mathematical. So Dell relied on heuristics where optimization was needed. So the research goal, therefore, was not incremental improvement; it was fundamental redesign. It replaces the static 10-day rule with a dynamic service level driven inventory policy that adapts to real demand variability and lead time uncertainty. Before we go into the math, it is very important to understand where inventory risk is most concentrated. The study focuses specifically on the final stage of inventory, the revolvers. This is the last buffer before assembly. Dell pulls parts every 2 hours from these locations. That means any error in inventory planning here immediately affects production. So at the same time, suppliers replenish these revolvers only about 3 times per week, often from Southeast Asia, with lead times ranging from 7 to 30 days, depending on shipping mode. So we have extremely fast downstream pull, slow and variable upstream replenishment, and high volatile component economics. This combination makes precise inventory modeling absolutely critical. So yet Dell was using a one size fits all rule. This is the failure point that sets up the rest of the analysis. In the next section, we'll move from problem framing to how the system actually works and why vendor managed inventory, despite its good intentions, became a source of structural inefficiency.
Building on the foundation just laid, I'll now take you deeper into how Dell's supplier logistics center operate, why vendor managed inventory became problematic, and where the optimization opportunity truly emerged. Let's begin with the supplier logistics center ecosystem. SLCs are not warehouses in the traditional sense. They are strategically located, usually within minutes or hours of Dell assembly plants. Their sole purpose is to ensure that when a customer order arrives, Dell can pull exactly the right components in the right configuration almost instantly. From Dell's perspective, this system is brilliant. Assembly line pulls parts every 2 hours. Production remains synchronized with real demand. Finished goods inventory stays minimal. But from the supplier's perspective, the picture looks very different. Most suppliers are based in Southeast Asia. Shipping components to SLCs involves long lead times, batch shipments, and significant uncertainty due to customs, transport modes, and capacity constraints. Suppliers typically replenish SLCs only 2 to 4 times per week. That means they must hold enough inventory in the revolver to absorb demand variability, lead time delays, and Dell's internal scheduling fluctuations. Now, layer on Dell's inventory rule. Dell dictated a fixed inventory target, roughly 10 days of supply, regardless of how volatile demand was or how risky the component economics were. Suppliers were required to comply. This is where vendor managed inventory, which is often praised in textbooks, starts to break down in practice. In theory, vendor managed inventory aligns incentives by allowing suppliers to manage inventory more intelligently. In reality, Dell controlled the target levels, the pull frequency, and the consumption pattern. Suppliers controlled the financing, the depreciation risk, and the operational burden. The imbalance created a situation where Dell optimized its own metrics by externalizing costs. And here's the key insight: this wasn't malicious, it was structural. The system was designed to prioritize Dell's internal performance indicators without mathematically accounting for system wide cost. The research identifies this as a massive opportunity. By redesigning inventory policy, not increasing stock, not cutting service levels, Dell could reduce revolver inventory by 40%, increase inventory turns by 67%, and improve supplier economics simultaneously. That's extremely rare in supply chain optimization. Usually, cost reductions come at the expense of service or partner satisfaction. Here, the opposite happens. Why? Because inventory wasn't providing real protection. It was compensating for poor information and poor modeling. To demonstrate this, the researchers focused on a pilot component known as XDX. XDX is a high value, multi sourced component. Customers don't care which suppliers provides it. Dell can choose which supplier to pull from at any given moment. This makes XDX a perfect test case because it has real demand volatility, it involves supplier choice, and its economic impact is material. One of the most important variables introduced in this pilot is the attach rate. Attach rate measures the probability that a particular component is required for a given product configuration. For example, if 40% of high-end laptops require a specific XDX variant, the attach rate is 0.4. Small errors in attach rate forecasts create huge inventory distortions. Why? Because Dell sells millions of units. If attach rate is misestimated by even a few percentage points, suppliers either drown in excess inventory or face stockouts. To manage this complexity, the research made a few disciplined assumptions. Demand is forecasted using a rolling 10-day stationary window. Suppliers order in batches, and lead times are variable, not fixed. These assumptions are realistic. More importantly, they allow the system to be mathematically optimized instead of heuristically guessed. This sets stage for the core of the research, the QR inventory policy. Instead of saying hold 10 days of inventory, the new approach asks when should we reorder? How much should we order? And what service level is economically justified? This is where inventory stops being a blunt instrument and becomes a precision tool. In the next section, we'll dive into how the QR policy works, how reorder points are calculated, and why accounting for variability, not averages, is the real breakthrough.
Okay, now that we understand the structural problem and the ecosystem in which it exists, I'll walk you through the mathematical heart of this research, the dynamic QR inventory policy. Let's start with a simple question. Why did the 10-day rule fail so badly? Because it treated uncertainty as irrelevant. Traditional rules of thumb rely on averages, the average daily demand, the average lead time, and average consumption. But supply chains don't fail because of averages. They fail because of variance. The QR policy is built specifically to address that. Under a continuous review system, inventory is monitored constantly. When the inventory position, that is, on hand inventory plus on hand inventory minus back orders, falls to a predefined level R, a replenishment order of size Q is triggered. The elegance of this system is that it separates two decisions. One, Q handles ordering efficiency and transportation economics, and R handles risk protection and service levels. The real innovation lies in how R is calculated. R is composed of two components. One, pipeline inventory, that is the expected demand during the lead time, and two, safety stock, additional inventory to protect against uncertainty. In Dell's old system, safety stock was implicit and arbitrary. In the new system, it is explicit and mathematically justified. The reorder point incorporates mean forecast error, standard deviation of forecast error, mean lead time, and standard deviation of lead time. Crucially, the formula captures the interaction between demand variability and demand lead time variability. This matters because high demand during a long lead time is exponentially more dangerous than either factor alone. By modeling this interaction, the system avoids both overreacting to noise and underestimating the risk. What this means in practice is that the volatile components automatically receive higher safety stock when justified and lower safety stock when the information improves. This is dynamic but not static. But how do we decide on how much safety stock is enough? That brings us to New Zealander logic.
News vendor logic. Instead of choosing service levels arbitrarily, like 95% or 99%, this research uses news vendor economics to determine the optimal service level. The news vendor model asks a brutal, honest question: what is more expensive, running out of inventory or holding too much of it? These costs are quantified as underage cost, line stoppages, lost sales, expediting, etc., and overage cost, holding cost, and critically component devaluation. The optimal service level is determined by the critical fractal, which is underage cost divided by the sum of underage cost and overage cost. This is powerful because it forces trade-offs into the open. For high depreciation components, overage costs are huge, so the optimal service level may be lower than intuition suggests. For mission critical components that stop assembly lines, underage costs dominate, justifying higher service levels. This is not guesswork, it's economics. The research introduces a brilliant metaphor: inventory power, the theoretical minimum inventory under perfect conditions, and inventory handicap, the excess inventory inventory required to protect against uncertainty. The goal of management is not to increase par, it is to reduce the handicap. And the biggest contributor to the handicap turned out not to be customer demand but Dell itself.
The most surprising discovery in this research is what's called pull deviation, Dell's internal bullwhip. Even with stable customer demand, Dell pull components from suppliers in large, irregular, and uneven batches. This erratic pull forced suppliers to hold extra safety stock just to survive. By smoothing internal pull behavior without changing customer demand, Dell could dramatically reduce supplier inventory. To enable this, Dell built value chain stocks, a digital extranet that shared real-time inventory data, updated reorder points daily, and aligned forecast across the network. The result, 40% reduction in revolver inventory, 67% increase in inventory turns, $43 million net present value from XTX alone. The final message is simple but profound. Information replaces inventory. Supply chain excellence is not about cutting stock blindly. It's about replacing uncertainty with intelligence. Thank you.